All right, so I'm just going to go through a couple more examples of like running regressions in Excel, interpreting the coefficients, determining if things are significant. Kind of going to, go. There's not a huge structure to this in the sense that like I'm just going to kind of work through these examples and kind of take questions or things as they pop up. So, oops. So on Canvas, I put up a couple of these files. One of them was a little bit too large, so I'll kind of just work off my computer with that one. But I've got this traffic data and this shark attack data that we'll kind of start out with. And if we have time for the other one, because someone sent me an email, we will go over that. So the shark attack data, I don't even remember where I got this, but this is basically a data set. Looks like, we can investigate it a little bit. So one thing that's really helpful in Excel when you have a data set. So I'm gonna go to that very first variable. I'm gonna hold Control and Shift or Command Shift on Mac, hit over and then down. So notice that selects the entire data set. I've got about what, 3,600 observations here. I'm gonna go to the Data tab and hit this filter option. Okay. So when I scroll back up to the top, oops, after hitting that filter option, notice it kind of gives me these filters at the top. So real quickly, I can like look and say, oh, I've got some shark attacks as far back as 1779, and then, as recent as 2016. So I've got a bunch of different information here. Some of it, the way that kind of data sets come in will be kind of hard to work with. If we have a little bit of time today, I might show you a couple things with how you could kind of, I guess, call it clean the data. But we'll kind of keep it pretty basic to start out with. So I've got, the day, the month, the year. There's like a description of if it was provoked, were they boating, where it occurred, the age of the individual, whether or not the attack was fatal, and then some other information here as well, right? So one thing I might be interested in initially is trying to look at, can I predict kind of the bite size, right? And I forget exactly how this is measured. It's some really fine measurement. Obviously, there's some large values in here, so it's something even further down than millimeters, but we've got a really kind of fine measure of what the bite size was. So what I'm gonna do is some of this information is really difficult for me just to use because it comes in, it's not numerical, right? Anytime we run a regression, we can't run a regression with a qualitative variable. Now, I'll show you a couple things we can turn qualitative variables into quantitative, but for now, we'll kind of just focus on just using the quantitative variables here. So this is probably, I guess, best practice if you want to call it that. So I'm going to select the entire data set again. I'm going to copy it. I'm then going to go to a new sheet. I'm going to paste this because I'm going to kind of get rid of some of the information I don't need for this regression, but I don't want to delete the original data set, right? I want to keep that intact. So you go over here. So again, I'm going to filter this. I'm going to start getting rid of some of these quantitative variables. So I'm going to delete these. Oops, I just want to delete this one. I'm going to delete these. I'll delete these. I kind of simplified my data a little bit here. So maybe I'm thinking about, well, can I predict the bite size based off of kind of the length of, I guess, the shark, right? So let me switch this over to .cam and we can kind of pull that up as I'm working on things here. So I can just give you a little bit better of idea of what this will look like kind of written down, what I'm doing. Let's go back, there we go. So what I'm thinking about is trying to predict bite size based off of the length of the shark here. So I'm thinking about my Y variable, this kind of bite size here. And then I'm going to try to predict that based off of the length of the shark, right? That's the regression, the very simple regression that I'm thinking about. So go to data analysis here, scroll down to my regression, hit OK. My Y variable I'm going to select is bite size. Right? The X variable, I'm going to click here. I think because I have multiple things open, it's not automatically going to the top for me. It should do that. So here's the length variable. So I'm just going to Control Shift or Command Shift, hit the down arrow to select that really quickly. I selected the labels, so I want to make sure I hit that. I'm just going to put it on a new worksheet. All right, so hit OK. Then there's some other options down here. We never have to kind of mess around with those. Oh, sorry, you can't see this. I will make this mistake every single time. So, all right, there you go. So I kind of selected that Y variable. I'll kind of go back through that again. I selected that byte size, right? Control Shift or Command Shift on a Mac, and I just hit the down arrow. Right? It selected the entire variable for me. Again, I'm going to go to select my X variable. Notice, I think that's what I did wrong. So when I go back in, when I click on the little thing, it'll send me to the top of the data set there. So my X variable was the length, right? So I selected length, Control Shift or Command Shift on a Mac, hit the down arrow, click back here, it sends me back. I selected the labels and then just hit OK, and it spits this out at me. So I'm going to rename these. This was kind of our regression data that we kind of deleted some of the stuff we didn't need, and we'll call this our first regression. So let's zoom in on this so we can see the numbers a little bit easier here. So it's going to give me kind of all this output. Kind of the thing that I said really all we're going to focus on, we've talked about the R squared, and then we're going to focus on the kind of first 4 columns down here. So I'm going to just widen them so I can see the names just to make this a little easier as we're working through this. So it looks like how much of the variation in the byte size of these attacks am I explaining with just the length of the shark? Well, my R squared is kind of from 0 to 1. Right, representing the proportion of the variation I'm explaining in the Y variable. So if I want to turn it into percent, I think about moving the decimal point 2 places to the right. So I'm explaining the proportion of 0.06 or the percentage of 6%. So I'm only explaining 6% of the variation in byte size by simply including length. Right? But if we looked at this here, remember kind of our general interpretation is of the coefficient is a 1 unit increase in the X variable causes the predicted Y value to increase or decrease by the coefficient, right? Whatever that estimated coefficient is. So for us, when you think about what's a 1 unit increase in length, well, this is where we have to be given a little bit more information, right? I've got length here. I'm guessing this is in feet, right? But we would have to be told, like on the exam or something, I would actually give you an explicit explanation, but I would also probably put something like, I'm not giving you the data set, but I would say, here's length, and then next to it, like whatever the unit is, right? Feet, inches, however we want to measure that. So we've got length measured in feet here. So a 1 unit increase would be a 1 foot longer shark would predict the byte size increases by 155.7. And this is where kind of tried to go back, and I thought this was an interesting data set, but I couldn't find the original kind of explanation of the variables, and I can't remember exactly how byte size is measured, but let's just say it's millimeters, right? I know it's some really fine measurement. Okay? Now, because I don't have any other variables in this regression, that's where I'm done. Right? If I had additional controls, it'd be the exact same interpretation, except all else held constant in the regression. So this is a little bit of a naive regression because there's probably a lot of other things that kind of would influence, right? Just because you have different lengths of sharks, right? In different depths or in different locations, we probably have different types, which would have different kind of, sized mouths or kind of, we would expect bite sizes to vary. And so it's kind of a naive regression not to include any other additional controls here. Okay? So I could then maybe go back to my regression data and say, well, look, I know there's probably a lot of other things that matter. So maybe instead of just length, maybe I also want to include, what else do we have here? Let's do, we could do kind of the temperature of the water. This will probably pick up kind of differences in location. Was this, near the shore? Was this kind of out quite, pretty far from the shore? So we'll include this as well, right? So go to my data analysis, tab, go to regression, hit OK. Well, my Y variable, this is kind of nice because I already had byte size selected, but my X variable, I wanted length and I also wanted the water temp. So I might think that I could click on length, hold control, click on water, kind of the water temperature, hit the down arrow. But notice it's really only going down to the bottom of that second variable I selected. Now, even if I try, there might be some other ways. So maybe I go select this one, go up to the top, hold Control, hold Shift and the down arrow. Okay, now I've got both of these selected. But I'll show you why I went through this quick because it doesn't matter. If I hit this, I've got my label selected, I hit OK, I'm going to get this contiguous reference error, right? So running regressions in Excel isn't ideal. Right? Usually we would use other statistical programs. It just makes it a little bit easier. So in Excel, one of the limitations is I can't run a regression with multiple X variables unless they're right next to each other. Now that's okay. It's going to take me a little bit more work, but all I have to do is, click on this length column and move it right next to that water temperature, right? Because those were the two I wanted included. So now, when I go back to my regression, I've still got my byte size selected as my Y variable, but now my X variable, I'm going to select both of these, right? Length and water temperature. Hold Control Shift or Command Shift on a Mac, hit the down arrow, it selected both of them, got my label selected. Now it can run that regression. So they just have to be in like consecutive columns. There can't be any columns in between them. So now if we look at the output, right, we can see, well, we're not explaining a whole lot more of the variation, right? If we compare this, 6359 to our original one, 6358, right? So, adding in the water temperature doesn't, I'm going to just rename this here real quick to regression 2, doesn't really allow me to explain that much more of the variation. And if I look at this, it kind of makes sense because now if I look at my coefficients, right, I can interpret these, and I'll do that in a second. But if I'm trying to determine whether or not they're statistically significant, if I look at these p-values, remember, we only reject the null if the p-value is less than alpha. Okay? Well, what's our null hypothesis always starting out? We said for these regressions, when we're looking at these coefficients, we always start out assuming that they're equal to 0, right? That there's no relationship between our X, and Y variables. So that makes the alternative that's not equal to 0. So if I have a p-value of 0.88, that's not going to be less than any of the alphas we use, right? It's not less than 0.1, it's not less than 0.05, it's not less than 0.01. So I can't reject the null at any level. And if I can't reject the null, I can't reject that the true relationship between water temperature and byte size is anything other than 0, that it even exists, right? So I didn't find any evidence here that the water temperature is correlated with the byte size. Remember, I say correlated there because these aren't causal, right? These aren't evidence of a causal relationship. The more controls we add in, the closer we're getting, right? We're eliminating some of that bias we talked about by when we have these important variables we've omitted from our regression or not included on our right-hand side, but it's still only evidence of a correlation. Right? So anyways, we failed to reject this. So what we're really saying is, yeah, water temperature doesn't allow me to really make any better predictions about byte size because that true relationship between the two could be 0. So knowing the water temperature doesn't allow me to make any difference in the prediction of what the byte size is. So, if that's not a significant relationship, when I added that into my regression, it shouldn't have, I shouldn't have really changed my R squared. I can't really explain any more of the variation in byte size when I include both these variables than when I just included length, right? Because that water temperature is just insignificant, right? I can't reject the null that it has any relationship to my Y variable. Okay. Now I could go through and kind of still do the interpretation, right? Even though I found evidence that there is no correlation, the interpretation would be a 1 unit increase in our X variable. So if the water was 1 degree warmer of water, would predict, I don't know why I put a comma there, would predict the byte size decreases, right? Because we have a negative coefficient there by 0.75 millimeters. I mean, first of all, that's the size of that effect is almost nothing, right? And it's statistically insignificant, okay? So we can start to make the, rejection decisions based off this p-value. Just a reminder, right? When we see a p-value like this on length, Length is a really good predictor of bite size. Seems pretty intuitive there. The p-value is pretty much 0. So we could say that we can reject the null at every single level, which if we're rejecting the null, we're saying, yeah, I'm rejecting that there's no relationship. Or in other words, I found really strong evidence that there is a relationship between length of the shark and the bite size. That makes I mean, like I said, that just makes a lot of intuitive sense. So I could, from there, if I really wanted to, I could start to include a lot of these other variables in my data set. So, maybe I've got water depth. I can include that as well. So I'm just going to move that over. I've got the time. I'm guessing this is kind of military time representing the hour of the day. I've got the age of the individual. I don't know why that would influence the kind of bite size there, but maybe it could. And so I could, go to my regression tool. I've got that bite size still as my Y variable. But now I'm going to include just all these, 5 different variables now. Select them. Got my labels selected, put it on a new worksheet, move this over, call it regression 3, zoom in on the results, and it looks like, right, none of these variables seem to be real great predictors. My R-squared hasn't hardly went up at all. So I guess just before we even look at the results, if my R-squared hasn't changed much by including these new 3 or 4 additional variables, that probably tells me those variables weren't very good at helping me make more accurate predictions, or that there probably isn't a very strong relationship between those variables and the Y variable. So if I'm thinking about, well, am I going to be kind of rejecting the null on these, that they, the relationship is something other than 0? Probably not, right? Just based off of looking at the change in the R-squared. If I go down, sure enough, if I look at water temperature, water depth, time, and age of the individual, all these have extremely high p-values. I'm not really finding that they're really helpful at making accurate predictions about the bite size at all, which kind of makes sense. Like maybe water depth I would have expected maybe had a role, but time and age, I mean, the age of the individual isn't gonna, I don't know, maybe there was some relation, like, I don't know, sharks like to, bigger sharks like to bite older people or something like that. But I don't, going into this, I wouldn't expect necessarily this to have any relationship. But the one, right, that intuitively would is the length of the shark. Still very significant. Right? So, there wasn't a lot of other additional kind of quantitative variables in this data set. So it was really hard to add in a lot. But, even with this, the interpretation on our length coefficient now becomes 1 foot larger of a shark increases the bite size by 155 milliliters, holding constant everything else. So this age of the individual is the same time of the day, same water depth, same water temperature. We would expect the bite size to go up by 155 millimeters if the length of the shark goes up by 1 foot. So that was kind of the additional thing that gets added onto the interpretation when we have several variables, is it's holding everything else in the regression constant, right? Which makes this a little bit more powerful of an interpretation. Okay. Now, if I go back to this original data, I'm going to show you something that we can kind of do to quantify some of these qualitative variables. So I'm going to do this fatal, right? So all this is a fatal just means if it's a Y, it means the individual died from the shark bite. If it's an N, it means they didn't. Well, I can't really use this in my regression. It's not quantitative. But someone either died from the shark bite or they didn't. So this could be kind of coded as a 1-0 variable, right? One of these binary or these dummy or these indicator variables. So I'm not necessarily going to expect you to do this like on a homework or on the exam, but kind of today's I'm just kind of showing you a little bit more of what the power of regressions are, how far we can take it, and then we'll kind of start on some review on Wednesday for the exam. So I'm just going to call this fatal, right? I'm going to put an equal sign, and I'm going to use an if statement. I'm going to say, okay, if this is equal to a Y, right? Then that means the individual died from the attack. I'm just going to mark that as a 1. Right? So if that statement is true, I'm going to put a 1 in here. If it's false, I'm going to put in a 0. So basically what this would do, it would take this variable where the only 2 responses are N and Y, every time there's a y, it turns it into a 1. Every time there's an n, it turns it into a 0. And just to kind of make sure, those are the only two, right? If I use that filter tool and kind of just click on that, I can see that those are the only two responses here. So I have that in for the first observation. If I click on this cell and get this plus sign to be like this bolded black plus sign, and I double left click, it fills that in for the rest of the data set. Notice when we finally have a y, we get a 1 in there. When it's an n, there's a 0. Now, I don't want to, so outside of this class, what you'll find out is for these dummy variables, there's some issues running the regression in Excel if you use a dummy variable as your y variable. Now that's okay for us. We'll just act like Excel can do it because a lot of these other statistical programs are able to do it no problem. There's just a little bit more going on behind the scenes that Excel's not able to handle, but we'll act like it is. So you don't have to kind of worry about that. But if you try to do this, I don't know, in your next stats class, they might be like, well, you have to hold off on doing this in Excel. We need another stats program. But we can still get Excel to do this. There'll be a little bias in there, but we can ignore that for the sake of what we're doing. Okay. So what I'm going to do is I'm going to say, okay, look, I'm actually going to try to predict whether or not this shark attack is fatal. And I'm going to try to predict that just using all those other, right, the length of the shark and all those other variables that I had in there, okay? So now I'm going to go to my data tab, data analysis, regression. My y variable, I'm now going to select as this fatal variable, right? So Control Shift or Command Shift on Mac, hit that down arrow. Go back up to the top, I'm going to go hit my x variables. Well, I already moved these all next to each other, so I'm just going to use all these, okay? So select them all, Control Shift all the way down, or Command Shift on the Mac. Got my labels selected. I'm going to put it on a new worksheet. Hit OK. I'm going to zoom in so we can see this a little bit easier. I'm going to rename this to the fatal regression, just so we can kind of navigate these tabs a little bit easier. Now notice, you would think, if I include things like bite size, the length of the shark, the age of the individual, you'd think I'd be able to make a really good prediction here. My R squared is only 0.004, so I'm only explaining 0.4% of the variation. So we can interpret these results, but we should be very cautious, right? Because there's still 99.6% of the variation in whether or not someone is fatally killed in a shark attack that we can't explain, right? Or that we haven't explained using just these variables. But we'll stick now kind of interpret them and see which ones is there evidence likely have a pretty good correlation. Okay. So if I look at this first one, this is bite size, right? Now we had this one was where it kind of, what's the units on bite size? Well, I think that they're millimeters. So the bite size goes up by 1 millimeter. The predicted probability, right, when we have this 0, 1 variable, we can now interpret these coefficients as the increase in the probability of the y variable, right? Going from 0 to 1, right? So if the bite size goes up by 1 millimeter, the expected probability of whether or not this person dies from this attack only goes up by what? 0.000018, right? We move that decimal point 5 places to the left. Now, it's a pretty small effect, but 1 millimeter larger in the bite size, probably won't have that great of effect. So what if it goes up by, if we look at the original data on bite size, just to get an idea. So we're seeing it range from 0 all the way up to 30,000. So this might not even be millimeters. This might be something even more fine, right? So when I look at this, this is the effect of 1 more millimeter. But the range on this is like 30,000. Oh man, I need to edit this down. I think this is from the last couple of classes. So maybe I say, well, what if it was 1,000 millimeters larger, right? Well, if I know the effect of 1 millimeter, the effect of 1,000 would just be 1,000 times that coefficient, right? And now I start to say, okay, like a 0.01 increase in the probability of this being fatal, that's a 1% increase. That's not that small, right? Maybe it's a little bit more useful when we're making interpretations for more than just 1 unit changes. when the unit is really small, right? Any questions kind of up on this so far? I know I feel like I'm rambling a little bit, so if you guys have any questions, make sure you're stopping me here. I just think hearing more of these kind of is helpful. So you've got that interpretation, and that's holding everything else constant. The age of the individual, the time of the attack, the depth of the water, the temperature of the water, the length of the shark, right? And if we got a p-value of 0.001, that's going to be less than really any alpha, right? It's less than 0.01, 0.05, and 0.1. So we would say it's significant at the 10, 5, and 1% levels, because it's less than all those alphas. And we can reject the null hypothesis, which is there's no relationship between bite size and whether or not the attack is fatal. We're rejecting that. Intuitively, that makes sense, right? The larger the bite size should increase the probability that it's a fatal attack. And sure enough, right, we're rejecting it with a pretty very high levels of confidence. If we look at the rest of these, none of them are really, I'm kind of surprised water depth isn't significant there, but none of the rest of these are really that significant. The length of the shark isn't, but that's probably largely because it's picked up in the bite size. It doesn't matter if the shark is 15 feet long, if he kind of barely, bites someone. So I don't know why I made the shark male, but he or she kind of bites someone. But the only one that we do have, and it's not significant at any of our conventional levels, but I want to kind of harp on this a little bit. So if we have a p-value of 0.12, that's not less than an alpha of 0.1. So at the 10% significance level, we fail to reject this. So, if I'm just making rejection decisions, I fail to reject the null here, and the null is that there's no relationship. However, that's good, that's correct, that's the right interpretation, that's the right rejection decision. But I mean, if we think about rejecting at a 10% significance level is like rejecting it with 90% confidence. Well, if you told me that, can I reject with like 85% confidence? Well, the alpha will be 0.15, my p-value would be less, so I could reject. So even though I can't reject at the 10% significance level here, I'm not very far away, right? So there's still some pretty good evidence here that the age of the individual is pretty strongly correlated with whether or not the attack was fatal. And that, once again, kind of lines up with probably what our intuition would be. Now, we can't say that, there's a relationship with the 90% confidence level or with 10% significance, but we shouldn't ignore this. The p-value is really close, right? What if instead the p-value was 0.100001, right? And we just barely failed to reject. Well, that doesn't mean we should completely ignore this result, right? I mean, it's pretty close, okay? I was just showing that to kind of give you an example. So, we don't find evidence that any of these other things are good predictors of whether the attack was fatal, but age is pretty close to being a good predictor. Right? And that's holding everything else constant as well, right? So even if it was the attack that had the same bite size, same water temperature, everything else, but the person was 1 year older, right? We would still see an increase in the probability that that attack was fatal. Not a large increase, right? 0.0003, but still an increase. And very close to being statistically significant. Any questions on this before we keep moving here? All right. So, I could play around with this some more, and maybe I could control for the month, and I could turn some of these other variables into quantitative. Like maybe I, create a dummy variable for was it in the USA or not? And was it in Australia or not? Or was it an unprovoked attack? I could kind of create these other quantitative variables based off of some of the qualitative variables I have. Probably a really important one here would be maybe kind of turning this species, making an indicator variable for each one of these. But for the sake of what kind of time in class here, it would take me some while to kind of code this up. You can imagine if you had more time, you could do that and really have this regression that has quite a few right-hand side variables, right? Okay. So the other one, hopefully we'll have enough time to kind of get to the regressions I wanted to on it. We'll do this traffic stop data, right? So this was up on Canvas as well. Kind of an interesting data set. I believe this is well, it's a large city in Texas, in the South. I'm guessing this is Houston. And it's got a bunch of different, it's got all quantified data, which is a little bit problematic because I need kind of the variable like explanations to know exactly what numbers for the reason of the stop correlate to, like, okay, what, I don't know, what was that, stop, but, sorry, what was the reason? A 7, I don't know what that means. It was, a 7 here might be something like failure to signal, and an 8 might be speeding, right? Or all the different reasons for the stop. But we kind of have all these other variables as well that are kind of interesting, like driver's age and kind of the years of service of the officer. So one thing might be interesting. So when a stop occurs, was a ticket given or was there an arrest? Right? So I've got a couple interesting variables here. So I'm going to look at officers' years of service and the driver's age just to start out. Okay. So let me go to the data tab, hit data analysis. Oh, someone had a question. If I can get back up to, there we go. Oh yeah, I will interpret the intercept coefficient on this next example, but yes, I will do that. So what's our Y variable here? Well, once again, we're going to use a binary variable, which is, was the person issued a ticket, right? So I'm going to select that ticket variable, select the Xers. I'm just going to look at driver's age and officer's years of service, right? Just to kind of start out here. Got our labels, we'll put it on a new worksheet, kind of rename it Regression 1, move it over here, and then zoom in so we can look at these results. So we haven't explained a lot of the variation, right? Only about 1% of the variation in whether or not a ticket was issued is explained by the driver's age and officer's years of service. However, they are good predictors, right? These p-values are pretty much 0, so we can say these are statistically significant, or we can reject the null, so we can reject that there's no relationship, or we found a pretty strong evidence that there is a relationship between, and kind of what we did here was whether or not a ticket was issued and age, and then kind of officers' years of service. Right? So if we go to interpret these, it looks like, okay, for every year older, right, if we think about the interpretation of the coefficient on age, a 1 unit increase in driver's age would be if a driver is 1 year older, the probability that they get a ticket goes down by 0.00 about 4, which makes sense. I mean, at least I know when I was 16, I was way more likely to get a ticket or probably not be as I don't know, maybe well perceived by an officer who pulled me over as I am today. So, this kind of makes sense. And it's holding everything else constant. So holding constant the officer's years of service, that's the expected decrease in probably getting a ticket if the driver is 1 year older. Now, the intercept interpretation, right, kind of the general form was, if all x variables are equal to 0, the intercept is the predicted value of our y variable. Okay. So here, this is where sometimes the interpretation of the intercept gets really weird, right? And this is a really good example, because how could a driver's age be 0, right? But that's still how we interpret it. Because, I kind of gave you an idea last class, like if we had a data set that looks something like this, something like that, right? We're only ever going to see, we're looking at age, we're only ever going to see drivers who are, well, hopefully 16 or over, right? But it could be that this line of best fit, right, if I try to draw that, well, that's going to end up with a negative coefficient. I know that if I'm looking at a probability, I can't have a negative probability, right? But that's because the data will never start this far back, right? So when we start to come up with predictions, kind of like we talked about last class, when I'm putting in X values for age, I'm never going to be putting in 1, 2, 3, right? The lowest I'm going to be putting is 16. So the lowest prediction I would ever get would be a positive value, right? It's just that in order to determine where that line of best fit is, my intercept would be negative. I don't think it's negative here, but that could occur. So the way we would interpret this is for a driver who is 0 years of age and an officer with 0 years of experience, the predicted probability of getting a ticket is what? 0.72, right? So it might seem a little bit goofy, like why does it start out that high? Well, maybe just the fact that you get pulled over, there's a high probability. Like if officers are issuing tickets at an average rate of 60 or 70%, well, that's where you might start out, right? That's the average. And then depending on kind of the different attributes of the stop, maybe you're a little bit more likely or less likely to get a ticket, right? So that's why that's probably so high. Okay, but that's how we would interpret the intercept. Even though it has a goofy interpretation here, that's still what we're doing. Right? It's a very literal interpretation. Okay. Any other questions on this one before we keep moving? So this is where, and another interesting thing here, for every year longer the officer is kind of on the force, looks like they're more likely to issue tickets. So I guess next time you get pulled over, hope for a young officer, I guess. So, but we're leaving a lot of important factors out here as well. We could go back here and start to include some other variables here, like the gender of the driver, the reason for the stop, if we could figure out exactly what these numbers meant. But the one thing that I think is kind of interesting and it really kind of shows the power we could start to do is think about whether or not the officer is kind of white or non-white and the driver is white or non-white. So if we include these indicator variables, we can start to think about things like, is there discrimination going on, right? I mean, regressions would allow us to see look, if I could hold constant and say drivers of the same age, officer with the same years of experience, but the officer is white or the driver is white, what would the change there in the probability they get a ticket be? Well, that might start to show me evidence that there might be some discrimination going on. Now, when we go ahead and do these, this is correlation, right? There's a lot of other things we want to control for, but just kind of giving you a setup for the things that could be done, especially if we had a little bit more information here on kind of what these results and the reasons, or sorry, not results, the reasons for the stop were. And I think maybe I should go back here. At one point in time, and this is where that select the whole data. I think actually I might have had the original data set was much larger. I think I took out every other reason. And I think 7, yeah, I did. So these were all just for common traffic violations, right? So there wasn't suspected gun in the car or anything like that, right? So we're trying to compare otherwise pretty similar stops. So we'll go up here to data analysis, regression. I've got my Y variable, which is whether or not they got a ticket. And then I will select these 5, right? So, and actually I could even select these 6. So I'll do the driver is kind of male here. So I've got a 1-0 if the driver is male, a 1-0 variable if the driver is white, 1-0 variable if the officer is white. And then I created this other variable here, and I'll show you the name in a second. But it's basically, were the officer and the driver white? Right? So this might be some kind of, maybe if I think that, white officers are less stringent on kind of white drivers, maybe I'll see a negative coefficient there, right? They'd be less likely to issue a ticket. But I'm going to select all of these as my X variables. Go back up here, hit OK. So we're going to look here. And because I selected the labels, you'll kind of see it's nice. It shows me all those names. Right? Oh, actually, sorry, I misspoke. This was a 1-0 if the officer was white and the driver was non-white. So kind of working the opposite. Show us if white officers are giving tickets out at higher rates to non-white drivers. So if we look at these results, the driver's age and officer service still have the same signs. They're still really significant. So that makes sense, right? We've increased the R-squared to about 3%. So we can explain 3% of the variation in whether or not a ticket was issued with our X variables. And if we're looking here, it looks like if the driver is white, right, doesn't have a significant change in whether or not they were given a ticket, really high p-value. Looks like if the officer is white, right, pretty statistically significant effect, and it looks like they're less likely to issue tickets just in general. And I don't know what the explanation behind this is, but that's what the data is telling us. But the kind of interesting result here, like the one that would allow us to identify some kind of evidence potentially of discrimination, is if the officer is white and the driver is non-white, so this would be a 1 when that occurs, so 1 unit increase, well, our X variable now is a 0 or a 1, so 1 unit increase would be going from a situation where the officer's white, where any other situation where the officer isn't white and the driver isn't non-white, to when the officer is white and the driver is non-white. Right? So kind of think about this as when we have that combination of kind of race of the officer and the driver, here's the predicted increase in our Y variable. Well, our Y variable was a ticket issued. So the probability a ticket is issued is about 5% higher, right? An increase in the probability of 0.05 when the officer is white and the driver is non-white compared to all other situations. And that p-value is very close to 0. This is a statistically significant effect. And not only that, that's the interpretation holding constant everything else. So 2 drivers, right, who are both either male or non-male, both white, the officer was white, or in this case, we would have to have, in both situations, the officer is white. In both situations, right, we would have whether or not the drivers are kind of white or both non-white here. The driver's age is the same, the officer's years of service is the same, but the officer is white and the driver is kind of non-white. Right? It gets a little bit tricky with the interpretations of interaction terms, which I'm not going to like put these on the exam or anything, but just kind of showing you the power. Holding all that other stuff constant, when the officer is white but the driver is non-white, here's the expected increase in the probability of getting a ticket. Right? Now, just bad news, right? Because this is evidence of discrimination potentially going on. And it's statistically significant. But I was playing around with this data and I found this and I was like, we don't have perfect controls here. We could do a better job of controlling for some other things. But at the very least, after that bad news, I'll show you at least from the data what is maybe a little bit good news, right? So if we go back to this regression, we hit our regression tool, I'm going to do the exact same regression. So I'm going to include the exact same X variables, but I'm going to change the Y variable to not was a ticket issued, but did arrests occur, right? So I'm going to see now, is it more likely that the individual is arrested if the officer is white and the driver is non-white? Okay. So I hit OK, I get my regression results. Oh, I need to go view, zoom in. Notice we can explain much less of the variation in whether or not there was an arrest, right? That R squared is 0.004. When we were looking at, the R squared of whether or not a ticket was issued, we were at 0.03, right? So these variables allowed us to explain a lot more of the variation in whether or not a ticket was issued as compared to whether or not an arrest occurred, which kind of makes sense. There's probably a lot of other factors that matter, whether or not, previous history of with the law or something like that. But when we look at these results, when we go back down here to this officer white, driver non-white variable, well, once again, holding everything else constant, if the officer is white and the driver is non-white, so relative to all the other combinations we could have there, right? Officer being white and the driver being white. When the officer is white and the driver is non-white, there's about a 0.0024 predicted increase in whether or not an arrest occurred on that traffic stop, right? However, the good news is that p-value is 0.39. So really, we can't reject the null, or said differently, right? We can't reject that relationship is anything other than 0, which is good because that means when the officer is white and the driver is non-white, we can't say that the predicted or the probability that they get arrested is any different from any other situation, right? So if I'm looking at this, I guess, if we're trying to kind of paint a broader stroke or kind of summarize it, there may be evidence of discrimination occurring based off of just some correlation, right? It's not causal. There's correlations with whether or not someone gets a ticket and the officer is white and the driver is non-white. But there's there's not strong enough evidence to say that there's any relationship between whether or not someone is arrested and the officer is white and the driver is non-white, okay? So I don't know. This is, like I said, this is looking at kind of some of the studies that are out there, this is a much more simplified and kind of an analysis that has some flaws to it, but it is at least kind of maybe some starting evidence that we do have maybe some discrimination going on, but at least it's not going on at as extreme levels of, someone getting arrested, right? Now, someone getting issued a ticket is not, be more likely to get issued a ticket based off of race is not a good thing by any means, but at least, it's not kind of escalating to the point of arrest. Any questions over kind of anything here? I know we got some a little bit different interpretations thinking about, when X variables are binary or 1, 0, or when our Y variables are binary, 1, 0. The interpretation of the coefficient changes a little bit, right? Because it increases in the probability, because our Y variable, the units, really is probability, right? It's no longer, the Y variable isn't in feet, it isn't in, years, it's 0 or 1. So it's representing kind of a probability. Okay. We can go through and we can look at the other ones. Looks like male drivers are a little bit more, this is a p-value of 0, so they're a little bit more likely to get arrested when they're pulled over. I'm not wildly surprised by this. We could kind of go back and look at the ticket as well. Actually, their driver kind of gender doesn't look like it matters at all, because the p-value is higher. But yeah, we could do some pretty interesting interpretations like this. Start to analyze some pretty important issues. I would argue this is a really important issue, right? Of whether or not discrimination is occurring with traffic stops. So those are the two that we'll go through today. Someone asked me about this. If we have time, we'll do some review on Wednesday and Friday for the exam. In my other section, tomorrow, I'll probably go through slightly different linear regression examples than what we did, some different data sets. So I'll probably be posting today's video up on the YouTube page, but tomorrow when I go through my other section, I'll post their video up there as well. So you'll get kind of, if you want to, there'll be some additional data sets and regression analysis that I work through there. And then I've got the exam written, so it's gonna be, well, I'll go over a little bit more of the details on Wednesday because we're kind of running out of time here, but it'll be about 15 multiple choice, 2 short answers kind of with multiple portions to them. But I'll talk a little bit more in depth and in detail about those once we start going through the practice exams on Wednesday, Friday, and Monday of next week, and the exact kind of times the final will be open. I can tell you right now that I'm kind of planning on Monday, Tuesday, and Wednesday of finals week. It'll be kind of, you can get on at any point in time and take the exam during that 72-hour time period. We still will be doing some last minute review on Monday, so my suggestion probably would be wait to take it after we do that. But it will be available just so I know how scheduling and things get crazy around finals. So I want to make sure there's a pretty wide window open when you can get on and take that. Very similar to the last exams. Once you start, you'll have an allotted amount of time. I believe what I'm going to end up setting it at is 120 minutes, so 2 hours. So timing shouldn't be an issue at all in the final. Other than that, that probably does it for us today. We'll kind of start with some more exam review, going back, probably doing more hypothesis tests, reviewing some older stuff on Wednesday. Any questions from me before we wrap it up here? Okay. All right. Well, we will see you on Wednesday.